Morning, and it's a great pleasure to introduce this speaker for one lecture. This is Professor Tadmor. Professor Tadmor is currently a professor of aerospace engineering and mechanics here at the U of M. He received his BS and MS in mechanical engineering from Technion and a PhD in solid mechanics from Brown. Professor Tadmor has made seminal contributions in development of a multiscale theory and computational methods. And he has published 2 textbooks and over 50 papers, and he is really the authority in this field. So with that, let's welcome Professor Tadmor.
Thank you. All right. Thank you very much for the invitation. It's great to be here. It was a long trip, but I made it safely across the common. So I'm going to talk about kind of work we've been doing recently in my group on multiscale simulation. And it's going to be sort of an overview talk on lots of different things that we're doing rather than diving really deep into one particular thing. So I'm going to switch from topic to topic as we go through this. And I'm touching on a lot of work from different people, so I'm acknowledging their contributions here and funding from the NSF and Army Research Office, for which we're grateful. So the overall theme of the talk is about how do we deal with, how can we inform constitutive models, phenomenological engineering constitutive models, with more fundamental atomistic information. And at the continuum level, we think of a continuum of a material as a continuum, like a piece of copper is copper, and if you cut it into 2 pieces, you get 2 pieces of copper, and so on. So it's this sort of infinitely divisible material. And then in typical engineering, you characterize the behavior of these materials, and more recently nanostructures, by doing experiments, and then you see their properties, and then you go from there. But of course, we know that materials are actually made up of more fundamental structure. In particular, they're made up of atoms at that scale of abstraction. And there are a lot of atoms in things. So really, a material is not a continuum in the way we think of it. It's a dynamical system made up of many, many atoms. 1 gram of atom has 10 to the 22 atoms, or 10 sextillion atoms. I found out that's the extension for that. So 10 sextillion atoms in 1 gram of copper. These atoms are at very fine separation. Their separation is of the order of 10 to the minus 10 meters, or 1 angstrom. And their time scales at which atoms operate are also much, much faster than the macroscopic time scales we're interested in usually. The vibrational frequency is of the order of 10 to the minus 15, or a femtosecond, whereas, of course, typical processes are much longer time scales for us. So the question is, how do we connect between these 2 different gaps? And there are all sorts of questions related to that. So I'm going to pose sort of key questions in this area, and then I'll go through a few of them and give you some details of how we think about that. So the first one is, if we're going to model things at the atomic scale, how can we model the interactions between the atoms? Instead of a fitted constitutive model, we need something to characterize the interactions between the atoms. Once you do that, now you have these large numbers of atoms and you characterize their interaction, you find that the response is exponentially complex. The possible behaviors of the system is huge, and we need to think about how to deal with that. Then there's the obvious thing, which is that we want to go from small times and small separation length scales to macroscopic times and scales. And so how do we make that connection? That's the third issue. A fourth and a fifth that I'm not actually going to talk about in this talk, but that we work on. One is related to how do we relate macroscopic concepts to microscopic ideas. So concepts like stress or heat flux or things like that at the macroscopic or continuum level, what are those actually at the atomic scale? Type of ideas, and I won't have time to go into that really. And then a real big problem is non-equilibrium processes. So a lot of the methods that we do have are really limited to equilibrium or near equilibrium conditions. And once you go into non-equilibrium, there are issues. So I characterize these as sort of basic questions in the area of multiscale modeling that are of interest and people are studying all over the place. And so I'll just show you our take on this. So let's start with the first one, and that's the interactions between the atoms. So basically, atoms bond to each other. When you bring 2 atoms together, they form a bond. And that has to do with the fact that when they come together and they share their electrons, they can reduce their energy. It's because they reduce their energy that bonds form. Otherwise, nothing would ever bond to anything. So they come together, and they can go to a lower energy state. And that's really what quantum mechanics describes, is how these atoms come together and form bonds. Now, what helps us model these interactions is something called the Born-Oppenheimer approximation. Basically states that if you think of this kind of naive picture of an atom consisting of a nucleus and an electron, the nucleus is significantly more massive than the electron, like a factor of 2,000 or something. And so what happens is that as the nuclei move around, the electrons are very rapid and have time to adopt their ground state as the nuclei are kind of lumbering around and moving on that scale. And so that means we can do a separation. We can separate between the behaviors of the nuclei and the electrons. We don't have to solve the problem together. And that allows us to actually create models only in terms of the positions of the nuclei without explicitly worrying about electrons. That's sort of the key feature of quantum mechanics that allows us to do that. So it starts with the Schrödinger equation. So the Schrödinger equation is a wave equation that describes the probability density function of the probability of finding an electron at a particular location. And in general, this wave function or probability density function is a function of positions of electrons and nuclei. That's before you do this separation. So this is the general equation for the whole system. And you see there's an operator acting here, and this includes the kinetic energy of the electrons. And then you add to that a potential, which is the potential exerted by the nuclei on each other and on the electrons. And so you need to solve this equation. And if you look at this, you see that this is an eigenequation, right? You've got something times psi equals epsilon times psi. And so you can solve for the states, and that's really the quantized states that we're all familiar with. But subject to the Born-Oppenheimer approximation, if the nuclei are really moving very slow, then what you're always interested in is the ground state of the electrons. So not the excited levels, but for a snapshot of the nuclei, the electrons always have time to find their ground state. That's the Born-Oppenheimer approximation. It's not always correct. There are many processes where this is not correct, but for typical things that we are interested for solids, it tends to work well. So that means that we can write down a potential energy, which only depends on the positions of the nuclei R, and that can be composed of two parts. One is the nuclei interactions with themselves, and then part which is the ground state of the electrons for that set of positions of the atoms. So this idea that you can write a potential in terms of positions of nuclei is related to that. So you see there are no electrons in the picture anymore. So in principle, if you could compute this, if you could solve for epsilon 0, you could have a model for any arrangement of atoms that you want from which you could solve any problem you want. And this is done. I mean, these are, physicists and chemists solve these problems on a regular basis. Physicists use density functional theory to solve this, but it's an expensive calculation. And state of the art is of the orders of hundreds or thousands of atoms is what can be done. Typically hundreds, but you can push it with big machines and good algorithms. And so instead, what's often done is you replace this exact expression with an approximate expression. And so we don't know what this is, so we invent a functional form, v tilde, which depends on the positions, but also some parameters. And that functional form is really like a constitutive relation in mechanics. It's trying to model the interactions between the atoms using some phenomenological form with parameters that then you fit to more fundamental models, either DFT or experiments. So the simplest one you could imagine is called a pair potential. That's a situation where every particle, your phenomenological model is as if it's computed, as if it's connected with nonlinear springs to its neighbors. And it interacts with some range of neighbors, which is denoted by this green circle. So this red atom feels everything within the green circle here. And the energy then is just a sum of the energy in each of these nonlinear springs that are mimicking the bonding that's happening between those atoms in some way. And this most famous, well, no, I guess maybe I'm skipping that even. So then this is a very, very simple model, but you can go to more and more complicated ones. So you can do a three-body potential, which also accounts for the angles between bonds, not just the distance. There's something called pair functionals, where you account for the bond environment, and it gets more and more complicated. And so that basically you're trying to add more and more terms to this expression, more and more terms. There's going to be a plus and a plus and a plus that model other aspects of the bonding. And you come up with some reasonable physics or physical model to do that. Now, as you do that, two things happen. One naturally becomes more expensive. The models become, there's more calculations involved in computing the energies. And second, they have more and more parameters involved in them, which makes fitting a problem in some cases. Because as you get models that have many, many parameters, you can get into problems of overfitting and things like that. And so we are trying to use that to understand problems that we're interested in physically and understand what are the limitations of these potentials. So this is one example. This is with a project with Jialiang in the department. And we're interested in understanding fracture of silicon. And so this is a MEMS device. You can see here the MEMS device broke right there. And this is a close-up of the fracture surface. And we'd like to be able to simulate that and understand what is the reason for the fracture and to characterize it so that it can be used in sort of higher-level statistics models. And so this is one of the projects we're working on. And so the first question you have is, what model should you use to characterize the atomic interactions between the silicon atoms? Which one could you do? You can't afford to do the quantum. I mean, you can see the size scales here. That's way beyond anything that can be done with quantum mechanics. And so the problem is that there are a lot of potentials for silicon in the market, as it were. Okay, so this is a partial list. I kind of got tired in 2012, but they come out at about, one a year on average, a little bit more than that. So since the 1980s, they've just come out there's a regular stream of these potentials. Each of these involves a lot of work. It's probably 2 or 3 years of work to develop one of these potentials, to define the form, try to fit it, see that it doesn't work, go back, change your form, choose your training set. It's a complicated, involved process. Now, each of these gives different predictions for silicon. They're all models of silicon, but they're all approximate to some level or other. And if you choose a particular one, like this one, Stillinger-Weber, it actually shows that silicon is a ductile material. So this is a double-edged notch of silicon. If you pull on it, you see these patterns here. These are dislocations that are being formed. And you just have a lot of plasticity. It's behaving like copper. It's not behaving like silicon. Right? Silicon, is brittle. If you drop silicon, you get a lot of silicon. A lot of little pieces of silicon. This thing wouldn't. It would just bend. And it wouldn't do that. But if you take another one, this one does break in brittle fashion. And so each one predicts different things. And one of the things we're trying to do is get a handle on how do we evaluate these things. So I'll give you one example from of how we think about these things from a different field, actually. And what we do is we're using ideas from data analytics and machine learning to try and understand all those predictions of those potentials. So imagine you have this huge pool of potentials with all their predictions. How can we learn about what they're going to do? The example that I'm drawing here is from actually 2D materials. So we also are interested in 2D materials. You're probably familiar with graphene. It's a 2D sheet of graphite, basically a 2D sheet of atoms that were conclusively proven to exist in 2005. There was a Nobel Prize awarded for that. And since this discovery, or this confirmed discovery, because there have been rumors before, many other 2D materials have been discovered. And so we have graphene, but there's also hexagonal boron nitride and molybdenum disulfide and so on and so on. So there's a huge amount of, you can imagine, half the world now is looking for 2D materials to try and understand them because they have amazing strength properties, they have amazing electrical, magnetic properties, optical properties. There's just a lot of excitement about these materials. And so as an exercise, we're looking at this particular material, molybdenum disulfide, and we're trying to develop a potential for it and try and see how can we evaluate its accuracy. And so we use what's called a three-body potential. So you see you have pairwise terms like I showed you before, and these three-body terms, which are angular terms. Doesn't matter what the form is. If you're really interested, you can see it here, what it looks like. But the bottom line is that there's a bunch of parameters that show up here. In the pair potential, there's an A, a P, a Q, a sigma. All these parameters show up, which you then fit to a training set. And so what we do, the way we fit this is we use a method called force matching. So you define, it's a least squares type of an idea. You define a cost function. And the cost function is basically the difference between the forces predicted by this model, which are denoted here as F, which depends on the configuration and the set of parameters that we're trying to find. And FM0 are forces that are obtained from first principles, from quantum mechanics. So we do a molecular dynamics, a dynamical simulation of quantum mechanics. And we watch a trajectory, and we get a bunch of forces for different configurations. And then we try and choose the parameters that give the best forces from the model that are in best agreement with the first principle. That's called force matching. Okay, so that gives us a model, and you know, that would be something you could then use to do simulations. But we're trying to get a better understanding of how good these parameters are and how the predictions of the model depend on the parameters. So to do that, you can think about curve fitting in a different way. So instead of thinking of it as a least squares approach, so here's the cost function with the least squares, right? This is just like f times some weighting function, which is just like a representing the weight you're assigning to each force, and then you minimize to get theta. Instead of that, you can use a probability theory type of understanding of this. And so if you think of this function f rm of theta as predicting the expected value of an observation. If you were going to make an observation, measure the force, like in the DFT calculation, this would be, the model predicts what would be the expected value, because every observation you have has some noise associated with it. So this is the model predicts the expected value. So then the measurement that we actually have, the force from the DFT, is then drawn from this probability distribution. So the probability that we actually got this force in DFT is we're assuming is normally distributed about this expected value with some variance. That's characterizing that uncertainty. So, and then what you say is the likelihood that you made all those observations. So m here is the number of configurations that we're fitting to. All of the probability that all of them showed up is the product of the probabilities of each of them separately showing up. And that's called the likelihood. That's the likelihood that we have measured all of those forces in the simulation given what we know about our model theta here. And that has this form right here. So it's a different way of thinking. So rather than thinking of minimizing a cost function, you can think of this as trying to maximize the likelihood. It's maximizing the likelihood that these observations were measured given your model. And you're trying to maximize it because then your model is as best agreement as possible with the observations that you have. So now what you can do is you can compute something called the Fisher information matrix. So the Fisher information matrix is the second derivative of that likelihood, really the log likelihood. And it's related to the curvature of your fit. And so if the curvature is small, that means that the uncertainty in your parameter is high. So you've got something like, you've got something that's very, very flat, and from that you're trying to draw a parameter. And so there's a lot of uncertainty in that parameter. If it's very sharp, then you have a good agreement. And so this Fisher information matrix carries in it important information. It carries not the eigenvalues, but the diagonal elements of it and the inverse diagonal elements tell you two very interesting things about your potential. Let's do this one first. So the diagonal elements of the inverse Fisher information matrix is related to the uncertainty in the parameters. So these are the parameters in our model. And the bar tells you how uncertain that is. So it's trying to tell you how good your training set is, basically. If there's a lot of uncertainty, it means that from the training set that I have, I can't fit this parameter very well. It's very uncertain. I have not enough information about that particular parameter. On this side, the diagonal elements of f, not inverse, but f, tell you something about the sensitivity of the predictions of your model for a particular parameter. So if you perturb one of these parameters, how much can you expect an observation to change? So they're two different things. There are a lot of information bottled up in that thing. And so here's one example of how you can use that. There's something called the Pinsker inequality that tells you if you have a model and it's based on a bunch of parameters, and now you change one of those parameters slightly, how will an observable change that you're predicting? And so the change between what you expect to see for some observable t, if you perturb one of the parameters, change theta to theta I to delta theta plus I, theta I plus delta theta I, that's what you would see for that new model, minus what you see for your current model, is bounded by this expression. It's the standard deviation in the parameter, and it's the standard deviation of the observable given your model theta I, times the change you put in, times the diagonal element of f for that parameter. And so you can do that, and here's an example. Remember, we're talking about a molybdenum disulfide sheet. It's like a sheet of paper. But because of thermal effects, this fluctuates. So that little sheet of paper is kind of constantly wiggling around if you were to look at it. That means it has some effective thickness, that sheet. And so we're trying to predict the effective thickness of the sheet. And in particular, we're asking the question, how will our prediction for the affected thickness of the sheet depend on the parameters in our model? If we change a parameter slightly, will that thickness change a lot? And so there's the definition of the property. It's the difference between the atoms on the top of the sheet minus the atoms on the bottom of the sheet. And then we see whether this is a good bound, and it turns out to be a very good bound. So when we compute the left-hand side from a molecular dynamic simulation, we find this number, and we predict, and so that's the change in the thickness. And on the right is what we predict will be the change in the thickness, and you see it's right there. So it provides you a bound. So what is this useful for? It means if this is a huge number, it tells you really can't trust this model for this particular property. Because very small changes in that parameter will give you completely different results. So that's not something you can use this model for. So that's how we use this to decide what we can use for one. Okay, so that was this example. And I'll just say that this is part of a much bigger project that we have that's actually run by myself and my colleague over there somewhere, Ryan Elliott, together with Jim Sethna at Cornell. And that's a big project called OpenCim, and it's all about understanding potentials. What are their predictions? Which potential to use for an application? This was an example of what I just showed you. And so I won't talk about this, but if you're interested, you can go to the website, opencim.org, and then just read about it. And if you're doing anything atomistic or anything like that, you should come talk to us, because we're really keen to work and collaborate with people on this. Okay, so that was the first thing. We have models. They're uncertain, and we can use ideas from machine learning to try and understand the quality of those predictions and when to use what and whatever. So that's one area we work on. The second one has to deal with this exponential complexity of the energy landscape. So here we're interested in nanoscale processes like, say, compression of a nano column. So if you take a nano column like this and you apply a load to it and compress it, so this is before you compressed it, this is after you compress it, you see that I haven't shown you the curve yet, but you get a kind of a load displacement curve that has a lot of little jaggies on it. It'll be on the next slide, which have to do with the nucleation of all these kinds of defects that you can see. And this is work, Julia Greer, for example, at Caltech does this kind of work a lot. Bill Gerberg here over there, he does that a lot here too, right? Nanoindentation and compression of nanopillars. So there's a lot of work in this area. People are also interested in lots of nanocolumns. If you compress a lot of them at once, you get these effective behaviors that are interesting. Now, one of the things that you notice is that the effect is highly stochastic and highly rate dependent. So these are the results. I think these are from Julia's group. And you can see that what this is a little nanocolumn of this diameter, 125 nanometers. And they push on it. This is stress versus strain. And you can see it goes up, and then there are these drops that you see. And those drops are associated with nucleation of defects. Dislocation nucleates, little microcrack forms, things like that. And if you change the loading rate, so this is at a high strain rate and a low strain rate, very, very different results. And so it's very, very stochastic. If you did this experiment again, roughly you'll see that this is higher, but you'll get a completely different set of zigzags showing up. It's very, very stochastic. And so the argument is, why is it stochastic? Well, it's very small. There are random distributions of defects that affect what's going to happen. The system is too small to get good averaging. And so every time you get 10 defects like this, the next time is 10 defects like that. And so it's very different responses each time, which is all true. But there's also a more fundamental reason for the stochastic behavior. It's not just that there are more defects, but that it wouldn't make much difference if there weren't a lot of options for the system. If the system could only do one thing, the defects wouldn't make that much of a difference. But the fact is that the system has a huge number of possible behaviors. And the defects that you have in it push it into one set of behaviors as opposed to another one. And so you can understand that from thinking about the potential energy landscape of the system. And so let's go back and define what that is exactly. So this is the function we were discussing a minute ago. This is the internal energy, which depends on the positions of the atoms. If you add to this the potential of the external loads, you get the potential energy of the system, just the regular mechanics type of an argument. And you notice that it depends on lambda here, and lambda is the loading parameter. So in the nanopillar, for example, we're compressing, and so there's some force or a displacement we're applying. So everything is a function of that delta, of that lambda. Now, if you have this potential energy, the gradient of that potential energy gives you the force on the atoms, and then you can do atomistic simulations. This is basically the whole field of atomistic simulations, is to compute these forces and do something with them. And you can just minimize those forces and look at configurations, static configurations. That's molecular statics. You can solve F equals ma, Newton's equations for all these particles in the system. That's molecular dynamics. Or you can do some sampling techniques like Monte Carlo. Now, all of these methods can be understood in terms of the features of this potential energy landscape. They're all basically, all of these things are exploring that energy landscape. That's what they're doing. They're different ways of exploring. So to think about that, now you need to kind of expand your mind here if you're not used to thinking about this. We have to define something we call a configuration space. So remember, I have n atoms. So to fully characterize my system, I have to give you n positions. Those are the positions of those n atoms, right? And now imagine, think of that as a point in a configuration space. So one point in a configuration space is the positions of all n atoms in the system. So you think of it like you have to think of, since every position has 3 degrees of freedom, there are 3n numbers that you have to provide. So you have to think of a 3n axes, and then you choose a point in that 3n dimensional space. That gives you a configuration. Okay? And then you imagine plotting the energy on this 3n dimensional space. So at each point in the 3n dimensional space, put a spot of color based on the energy. And of course, you can't draw that. Beyond 3, we can't visualize it, but you can imagine. And in 2D, it would look like this. If I only had 2 components, so if this was all I had, 2 components, one atom with 2 components, I could draw the energy like this. And then you'll see that you'll have minima, which are these blue spots. You'll have maxima, which are these red spots. And then you'll have transitions between them, unstable states. So in this picture, these are the saddle points here. So you can go from, I guess, from here to, no, I got it backwards. The red is the minimum. It has to be the minimum. Yeah, no, the blue is the minimum. That's right. The blue is the minimum. You go through a saddle point to another minimum. That's right. I'm okay. Same thing here. Blue over a saddle point to blue. Yeah, good. So now these minima and these saddle points in particular are interesting because they have clear physical meaning. Each one of these minima corresponds to an equilibrium state of the system. Some defective state, a dislocation. One of them, the deepest one, will have no defects in it at all. That's sort of the kind of a ground state. But then all the other possible behaviors are blue spots in this curve. The saddle points that you're seeing here are dividing surfaces. And those are the transition states. If you want to go from one minimum to another minimum, you have to go through a transition state, and that's the saddle point state. So we have this picture of all these minima. And then this is where I was talking about the fact that this is non-convex. If it was convex, there would just be one minimum, and that would be the end of the story. It would be a nice, simple system. It has only one option. It's non-convex, which means it's like this, and it's got many, many, many places that it can go. Now, what is many, many places? There was an estimate that was done by Stillinger and Weber in the 80s trying to answer that question. How many blue spots are there? And so they basically say, well, first of all, you have the number of minima that you have there'll be a permutation term here, n factorial. That's not really interesting. That just means you can swap 2 atoms, and it's the same configuration, because they're the same, right? 2 atoms are identical. So that's not particularly interesting. This one was the interesting one, and this they got from an argument about how many ways you can pack things together. So it's an interesting kind of topological argument that they make. The bottom line is that they get this as an estimate, and then if you take a gram of argon, which again, 10 to the 22, 10 sextillion atoms, there are these many distinct structural minima. That's how many blue spots there are. 10 to the power of 22, which is probably the biggest number I've come across, in any kind of real physics, right? I don't know how many stars there are in the universe, but this is a huge, huge, huge number. And that's just in 1 gram of argon. Number of different states that you can expect. That's what I'm talking about in terms of complexity. And so that's why when you compress your little nanotube, your little nanocolumn, it has lots of options, right? It has this many options. So very small changes will drive it to different places. So we're trying to kind of get a handle on this. I'm not going to say that what I'm showing you now is the way to handle this complexity, but at least it's a way to try and start thinking about it. So we took a little nano column here, and this is work with Subramaniam Padamana, my graduate student, and Ryan Elliott. And we took a little nano column, and we compress it, and this is nickel. And then we want to understand the behavior of the system. So if you just do a kind of naive atomistic calculation and you compress it, you get a curve that looks like this. This is stress versus strain. You go up a little bit in the beginning. Initially, there's no defects. It's just a perfect column. Then you hit a point where you lose stability, and boom, you drop, right? Because there's an instability. And in this particular case, these two shear planes have formed in the material. Those are the defects. If you're a material scientist, these are like dislocations of nucleated and gone through the material. Or just think of it as shear. It doesn't matter. So this is what's going on in terms of the stress-strain curve. In terms of the energy surface that I showed you before, what's happening is, initially when you're beginning to load this, you're sitting in some basin like this. And as you pull a little bit further, this surface changes, right? Because as lambda is changing, as you compress more, the shape of your energy surface is changing. So a little further higher up the curve, this minimum that you're in is still there. So the perfect state is still there. But look, you're getting additional states forming. Those are the defective states that are beginning to form. The one you're in is actually shrinking. In fact, what's happening is you're starting in a well that's gradually going shallower, shallower, and is about to flip over. And when it flips over, that's the loss of stability. There is no more solution associated with the perfect state at that point, not a stable solution. And so those alternative behaviors are beginning to form as you're still here. Now, if you don't have temperature, you can't get to them. If you have temperature, you could hop over a barrier and get to them. But without temperature, you're kind of stuck in this state. But eventually, you get to this point. This is now completely flipped over. It doesn't exist anymore as a stable state. And then you just roll down the hill to a new location, and that's the nucleation that's occurring. It's the same kind of thing that happens with buckling. It's the same idea. All right. So what we want to do is then we want to find not just this one solution, which happens to be we've randomly decided to roll into this hill. Remember, once this loses stability, there are many, many places to go. We want to get our heads around that. So this is where Ryan Elliott's specialty comes in, use a method called branch following and bifurcation, or continuation in mathematics, is where you can follow those lines. So what we really want to do, follow these lines, get to the instability point, and then find the things that come off of that point. And so that's what these methods allow you to do. They allow you to go through a line, get to a bifurcation point, this instability point, and then follow the paths that come off of it. And then create this network of roads, all the stable and unstable pathways in your system. That's what they basically do. And so we apply this method to our little nano column, and you get some pretty wild things. You follow it up. Here's the instability. But then we don't just drop we don't just drop to some random location. This BFP method allows us to go through the bifurcation point and follow the unstable path that comes out of it. And so this dashed line is an unstable solution. If you put your system there and you breathe in China, it'll fall off, right? So it's not stable, but it is an equilibrium solution of the problem. The interesting thing is that those have bifurcation points as well, and if you keep following an unstable path, it sometimes becomes stable again. And then it goes unstable and becomes stable and so on. So this is from the primary path. We get this whole complicated spaghetti thing, and occasionally we identify stable pathways. So here, this X is a stable pathway. You see, if I was to just keep the load constant and drop, that's a solution that I could get to. This is another solution I could get to. There are a lot of possible solutions. Now, these are all from the primary path. You can now go to the bifurcation point and look what comes out of that bifurcation point. And something else comes out of there. And so you get another line. And it has unstable and stable pathways. And then you go to the next bifurcation point, and you keep doing this again and again. And the nice thing about this is that this is trivially parallelizable, right? Each one of those pathways is completely independent from the other one, so we can just send it to a lot of computer processes. It's like what Alan Needleman at Brown used to call massively serial. It's a massively serial problem. We can run it on lots and lots of processes at the same time. So when we do that, we get something that looks like this. So you can't see, but there's lots and lots of things, lines on top of lines on top of lines here in this big blue region. And in fact, we think that this is probably the largest calculation of this type ever done. of this BFB type simulation, these continuation type simulations. So it's got about 200,000 pathways. Of those, 50,000 are stable, 10 million solution points, and it would take 9 years to run if we didn't parallelize it. But we have a nice parallel code, so we can run all of this in about a day. But otherwise, it would if you had on your desktop computer, it would take you 9 years to run this thing. And so what this is showing is all the stable pathways, all the saddle points, which are the transition states that exist. And so if you cut at any point inside of this, say at a load, at a strain of whatever strain I'm here, 0.18, if you cut, you'll find a lot of, you're crossing through a lot of lines, a lot of unstable lines and stable lines, and those define all the possible behaviors of the system at that level of strain. I'll show you a picture on the next slide exactly what that looks like. And so we define something we call the equilibrium map, and the equilibrium map is the diagram of all the possible behaviors of the system, stable and unstable, and plus something we call the kinetic transition network, all the transitions that can occur between them. So that's the connectivity. What stable state is connected to what stable state? So here, let me show you a picture. Here's a picture from a strain of 2.8%. So 2.8% is here somewhere. So I'm cutting right here, and this is showing you all the states that exist at that state. So here's the perfect structure right there. That's the one where no defects have nucleated. It's a stable state. And it's connected. All these red ones are saddle points. So if you, I don't know how well you can see that from far away, but you can go through this red state, which is a saddle point, to get to this defective state. Or you can go through this red state to get to this defective state. Or you can go through this red state to get to that defective state, and so on. So it's finding the possible behaviors of the system, where it can hop, how it can go from place to place. So this is characterizing the state-to-state dynamics of the system, what it can do. So if you maintain the strain at 2.8% and you just watch the system, it'll hop from these things from one to the other if you give it enough temperature. If you don't give it enough, it'll just sit here. It's stuck in this state. But if you heat it up a little bit, it'll kind of do a walk through these states. Okay. And so we identify all these connectivities. We associate a rate with each of them from transition state theory. So you probably recognize this rate type of expression. There's an attempt frequency and a probability of success. It's the standard type of expression. And so that would be sort of the rate of going across the saddle to this point. And then we have another rate of going across to this to this. And so you combine all these things together and you get a rate table. All the rates from one state to the other are all characterized. And everything in this expression is computed from the atomistic model. And we know the attempt frequency from the curvature at the basin, and we know the barriers, so we know everything. Okay, so then we can evolve the system using kinetic Monte Carlo, a stochastic method. So what you do is you go back to this picture. You start from some state, let's say this one, and then you have to choose where am I going to jump to. And kinetic Monte Carlo is a method to do that. Basically, you identify all the possible behaviors of the system. You choose a random number to choose one of them. You then increment your time based on what you would have expected to wait for that event to occur. And then you go back and you just keep doing this again and again and again. So this is a method for actually for reaching longer time scales. Because instead of just vibrating there, waiting for something to hop, I'm just cutting to the chase and just modeling the hops themselves. And so this lets you reach much longer time scales than regular. Now so this is standard kinetic Monte Carlo. A thing that complicates our lives a little bit is that we're not stuck at 0.18%. Our strain is changing as we're modeling the system. And so we actually have to take into account the fact that the load is changing as the system is sampling it. And you have to do a time-dependent, a KMC for time-dependent transition rates. So we have to construct a rate table at each time step and then basically use a method that's applicable to that. I won't go into the technical details that are written there, but you can do that. And then these are the results that we get. And so this is now the stress versus strain. And we can model at two different strain rates here. So these are the results from these kinetic Monte Carlo simulations. The red line is at a high strain rate. If we push this thing very, very rapidly down. And the blue is what we get if we go at a much lower strain rate. So this is a 10 to the 8 strain rate and 1 strain rate. And you see very different behaviors. In the high strain rate, what happens is your system basically gets stuck in whatever basin it's in because it doesn't have time to escape before you already reach the instability. Remember, if I just keep pushing long enough, it eventually just folds over and loses stability. But we're not, if you give it temperature, it could hop out. But if you load so rapidly that it doesn't have time to do that, it doesn't happen. And so you get the red curve. If you load slower, then you see it escapes before the instability point. It escapes earlier to some other state. And there's a lot more noise because it's visiting all sorts of other sites as it's doing that. So you get different types of behaviors. So I just explained that. And from a bridging scales perspective, by doing this approach, we can do a simulation that would take you 253 years on a CPU to do. We could do it in an hour because we're using both the kinetic Monte Carlo and this method to construct the tree. So this is one way of this connecting of scales that we're talking about. And just showing the experiments again, you see that qualitatively, even quantitatively, it's in pretty good agreement with the experiments. You see that at high strain rates, you get the curve is higher up. At low strain rate, it's lower down, and we now understand what's happening. It's escaping, and so on. So that seems reasonably good. OK, so this is the last topic that I'll cover. And this is really how do we scale across scale? How do we connect things, which is really where I started from in my PhD work, developing these sorts of methods. So this is a completely gratuitous picture. It has nothing to do with anything. I guess I'm in aerospace department, so I had to have an airplane. And I want a crack. And so there's definitely a crack in there somewhere. And by the way, nobody was killed in this accident. Otherwise, I wouldn't show it gratuitously like this, right? What happened was that something, it wasn't de-iced properly, and some ice flew into the engine, and the engine seized, and the thing crashed, I think, 75 seconds after taking off or something like that. But it was handled very well, and everybody survived well. OK, anyway, having said that, let's now focus in and see what this multi-scale nature of materials really is. So if the investigation team that came in here and looked at the damage in this plane, trying to understand what happens, they would make pictures like this, where they look at the damage at the tip of a crack. So this is really sort of the macroscopic crack that you can see in the system. There's the scale, length scale, 1.2 millimeters, 1,200 microns. But we're going to zoom in and see what's happening in the material at different scales. So if you zoom in at the very tip here, you're beginning to see some structure on a sort of, I guess, microstructural length scale. You could see sort of the features at the tip of this microcrack. There begins to be some scale associated with these steps that are going on. If you zoom in a little bit more, you're now at the tip of this crack, and you see that there's structure on the crack face itself. So this is on a smaller scale. This isn't changes in the direction of the crack, but this is changes in the surface of the crack. You can zoom in a little bit closer than that, and you can now see here's the tip of this crack here, and now we're down to the micron scale, and you see these things here. Those are grains in the material, so we're at the grain structure size now. And you can see that you're beginning to see the interaction of the crack with microstructural features. So here the crack has kind of broken through the grain, and here it's cleaved between the grains. And so there's an interaction having to do with the orientation of the crack and the grains and so on. You can also see some black lines inside of the grains here, and those are dislocations that exist inside the grain. So as the grain is propagated, it made plasticity, which are dislocations. And so we'll actually see that better when we zoom in one level lower. So now we're at 500 nanometers. Here's where this grain has cleaved through, this crack has cleaved through the grain, and you can see the pattern of dislocations that is formed around this location. Now we can zoom in a little bit more, and now this is it. As far as this talk is concerned, we've hit the atomic scale. So if you can see these dots, this is high resolution TEM, and these dots are atoms or related to atoms, depending how they took this picture. And you can see steps. These are now steps on the surface of the crack that are about, 10 atomic levels high or something like that. And now we're at 5 nanometers. So we're all the way down here. Now you could go lower if you wanted. You could go to the electronic levels and so on, but we're stopping at this point. So you see that this is a huge distance to go through, with not just in terms of distance and scales of time and length, but also in terms of the appropriate models to use at these different levels. There's a different physics being represented here. So one approach is to just do full atomistics. Just put in all the atoms and do that simulation. That's not practical because of the size issues. So The largest simulation done to date is this gray box. That was a trillion atom simulation. 10 to the 12 atoms. It was done with the spasm code in Tim Gurman's group at, is it Sandia or I always get the two of them confused. Either Los Alamos or Sandia. And a good thing this isn't being recorded so that I don't. Okay, so the length here is 2,500 nanometers. And you see, compared to the pictures I was showing you before, that was the one to last snapshot was 500 nanometers. So it's about this size. Gives you a scale. Okay? They did this. This was really a proof of principle. It was done on, at the time, one of the largest machines that existed called Blue Gene. 200,000 processors, 72 terabytes of RAM. Lennard-Jones potential. So that simplest pair potential you could imagine. Not meant to represent any real material of the simulation. Just kind of make the cheapest thing that you could do to go to the largest sizes. They were able to simulate 40 time steps. Each time step took 45 seconds of wall clock. You had to wait. Now, a typical time step is, in an MD simulation, is 1 femtosecond. That's 10 to the minus 15 seconds. And so if they wanted to do a simulation and reach 1 nanosecond, it would take them 521 days on this gigantic machine. If they wanted to run a millisecond, it would take them 1,400 years of constant computation on this system. Okay, so that's giving you an idea of why you can't just put all these atoms in and just run the computer and wait for the result. It's just not practical. I mean, there are many, many things you can do, but there are a lot of things you can't. All right. So here's an example. I'm giving you another example of the things we're interested in. And so we're interested in friction, and we'd like to simulate friction at the atomic scale. And so a way that this is often done is with an AFM, an atomic force microscope. You have a little cantilever beam, and it has a little pointer on the end like this, a little stylus at the end, and then you drag it on the surface. Really, actually, you tend to drag the surface underneath it. But anyway, you're pulling the stylus on top of the sample, and you're measuring the load and the forces, and that tells you a lot about the behavior of friction. And we'd like to understand and simulate that. Now, people have done molecular dynamics simulations of this, but because of what I showed you on the previous slide, they're limited to small sizes. They can't really model the whole apparatus. These things aren't huge, but they're about 100 microns. Remember that where are we with the state of the art? The state of the art is 2,500 nanometers. So that's a quarter of a micron. So there's no way you're doing a whole AFM this way. And so the simulations tend to be limited to just the very near tip region like this, and a little bit of the substrate, and then you isolate it from the rest of the world, and then you pull, and you do a simulation. And so there are some very nice simulations that have been done, but in many cases what they find is that their results are affected by this small scale that they can afford to model. In particular, a problem is that heat builds up in the system because of friction, and that heat is trapped because there's nowhere for it to go. And so that causes a problem. There are other problems as well. And so for that purpose, we work on a method called Quasi-continuum method, and that's a method that says, okay, I want atomic scale resolution here near the tip, but I don't need it anywhere else. But I want that model in there somehow. I'd like to model it. And so what you do is you use a continuum model of, say, most of the AFM tip and most of the AFM beam and most of the tip and most of the substrate, but you make atomistic region right near the contact area where the interesting physics is happening. And so what we do, this method allows you to do molecular dynamics in this region, where you're literally solving all the atomic interactions. And then you do a continuum model out in the far region. But the continuum is actually computed in a way that's consistent with the atomistic region. You compute the free energy density out in the continuum region, and that is computed from the same interatomic potential used in there. And so it's a consistent framework. And this is the stuff that goes back to my PhD, but we've been working on that for a long time since then to extend the capabilities of this approach. Now, this method, I'm not showing you any results from it, but it does work, and it allows you to dramatically reduce the number of atoms because you have a lot less degrees of freedom. You only have the nodes of your finite element mesh, and then some region right underneath, say, this indentar where you have atoms. And so I have a lot fewer degrees of freedom to keep track of. So for this example, we went down from 800,000 to about 4,500 degrees of freedom, or 3 times for degrees of freedom. But anyway, a major reduction, which allows us to do a simulation like this on one processor on a serial machine instead of parallelizing. And now we're working on a big high-performance code that will allow us to go to much, much larger sizes. But there's still a problem with this. So yes, we can go to much larger regions. You know, we can approach micron scales. We can actually go much bigger than this now. But we're still stuck with this time step. Because the MD machine, the MD integrator, clicks every femtosecond. And that means we're stuck with this problem of not being able to reach long time scales. And this is why if you open the literature and you read molecular dynamics simulations, they're almost always done at rates that are much, much higher than reality for the problem they're studying. Because let's say you want to break something. If you go 1 femtosecond at a time, you know, you'll run for a year and nothing you're not going to break anything because you'll just have slightly stretched it. So what you got to do is you got to pull it like that. You got to pull it at 10 to the 8th or something like that. You know, 10 to the 8th faster than is done in the experiment, and then you break it. But then you're also changing the physics in some cases, so that's not good. And so in this example here, this is exactly what we had to do. We did an indentation simulation, and we were loading at 5 million microns per second, whereas nano-indentation experiments are usually done, you know, 1 million times slower. They don't, you know, this is like firing a bullet into a very fast bullet into it. And the indentation is a very slow process. So we want to reach that. And so what we do is we've taken this idea of this quasi-continuum, this multiscale method, and we coupled it with another method called hyperdynamics, which is something that was developed by Art Voter at Los Alamos. And Voter is a chemist who originally did kinetic Monte Carlo type simulations and was frustrated by the limitations of those methods, their predictability, because you only got out what was in your rate table that I showed you before. He wanted to do something where the molecular dynamics themselves were accelerated. And he developed several methods for doing that. Hyperdynamics is one of them. And it's based on this idea. Remember, we talked about this a little earlier. If you're sitting in a basin and you have a little bit of temperature, what happens is you're bouncing around inside of this basin. Every so often you hop out. You go to a nearby one. And you're bouncing around in that one, and you hop out again, and so on. But the amount of time that you have to wait is related to this barrier that you have to go over, because that's the probability of success. And it's exponential. So high barriers means you're stuck in there for a very long time. And so in hyperdynamics, what you do is you add a bias potential to your system. So you take your real potential and you add a bias to it, which lifts up the basins. And when you lift up the basin, obviously you're going to escape much faster. In fact, exponentially faster, because it's all exponential. And now, of course, you say, well, that's a different material. You've changed your material, so who cares? But what you can prove is that if you bias them in a very special way where you don't change the dividing surfaces, then you actually get, everything happens faster, but at the same relative rates. So the state-to-state dynamics will be the same. You'll visit the sequence of states in the same probability in the accelerated code as you would in the original code. Okay, so the nice thing was that the way HotQC is derived, the method that I showed you before, lends itself, because it's based on statistical mechanics ideas, it lends itself to hyperdynamics, and we can basically use exactly the same idea for the QC method, and we can get this kind of boosting. So every time the clock ticks in our simulation, the real world time clicks by this amount, and you see that there's an exponential factor between them. So we click a femtosecond in our simulation, but it corresponds to a millisecond of real time, or something like that. So you can get much, much further along. And that's exactly what hyperdynamics does. And so we were able to rerun the simulation that I showed you before for this case, and you see the main point is right here, that we can bring the loading rate down to 10 to the 2 from 10 to the 6. And in fact, I think we're going to be able to reach further down than that. So we're already much, much closer to the experimental rates. And still working on this, but that's where we are with that. And these are what you see when you can account for rates in this way. So here is the depth at which you have to indent to create a defect. And you see that there is this is the rate over here, or the indented velocity. And you see that there's a strong rate dependence on the nucleation and so on. Although in this particular problem, there's no qualitative difference. They both show the same behavior qualitatively, the same kind of defects. It just nucleates at a different critical load. All right, and then I'll show you one more example, and then I'm done. Another direction that we're extending this method is for 2D materials. So I mentioned that we were interested in 2D materials. We have a Muri project on understanding, in particular, 2D layered materials. So I told you the 2D materials were interesting and people were excited about them. An area now that people are very interested in is stacking these materials. So if you have one 2D material, that's an interesting material. Special, mechanical, optical, magnetic properties, and so on. When you put two materials on top of each other, you get a new material with different properties. And the properties depend on which materials you choose to stack, because remember, you now have a whole, you have a menu of materials that you can stack, and the orientation between them. And so you have this immense configuration space to create new materials, something which is really new in what people can do technologically, right? You're not going to a lab and pouring in a little bit of sulfur or whatever to make an alloy. You're literally creating new materials by stacking existing materials. And you can even change the behaviors when you rotate. You can have, because there's the orientation between them can be easily controlled, you can have materials that are conductors like this and insulators when you rotate by some degree. So you can have all sorts of options for sensors and actuators and so on. So a lot of people are very interested in this. And so we're trying to understand, to model the mechanics and thermomechanics of these materials, and we're trying to understand how the orientation between them changes their behavior. Now these are kind of unique in the way that they behave. They're in plane like this. They're very strong. They tend to be covalently bonded. They're stiff materials, but bend very easily, like a sheet of paper. Hard to stretch, but very easy to bend because they're very thin. But the bonding between the layers is very weak. It's van der Waals, very, very weak, sloppy bonding between the two of them. And so for that reason, they're sometimes called van der Waals heterostructures. And so we're trying to model how what a stack of these things behaves like, and in particular, what happens if you have defects in them. And so we're going to this type of QC picture where we have each layer is modeled as a QC system like this, where we can have an atomistic region, say if there's a crack in it or if there's some other defect inside of it, and a continuum region. And so in the atomistic region, you would do full MD, just like I showed you before. Out in the continuum, you use some kind of an appropriate continuum model. We use a plate model because they behave like plates. And so the strain energy then depends on the membrane energy and the bending energy of the system, the Lagrangian strain in the element, and the curvature. And so you can literally write down a continuum model, or you can do something more fancy and compute things from atomistics. Either one works. In reality, actually, we find that the continuum model works very well, and we use that. And then you have an additional thing, which is that each of these layers has to talk to the layer underneath it through this van der Waals interaction. So we've constructed this system now, and we're beginning to explore its predictions. And I'll just show you the first kind of very preliminary results. If you put two layers of graphene on top of each other, and they're perfectly aligned, it looks like this. But if you rotate one of them on top of the other, you begin to get these patterns. You see that these patterns form. You can maybe pick them out here. These are moire patterns. And so when you have two organized structures rotated relative to each other, they create these long-range patterns. But the point is that in most places, they're incommensurate with each other. They don't fit anymore, which is part of the problem of modeling these systems. What's very interesting experimentally is that when you do that, if you take a layer of graphene and you rotate it on top of another one, the material is not happy. And so it undergoes what you can call an incommensurate to commensurate transformation. So all those regions here, these regions that are high energy, incommensurate regions, they try to to become commensurate with each other, to come to a low energy state. And that's what these triangles are. These black triangles that you're seeing here are basically regions where the material has kind of locally arranged itself to come into commensuration in a low energy state with the system underneath it. And this is the same picture, just where they highlight the interfaces. And when you zoom in, you get these types of regions where each of these triangles, you see, if you look carefully, you see you have a middle region here, which is a high energy AA type of a configuration, which is this state here. This is AA, where they're perfectly lined up. And it prefers to be in a BA or AB state where they kind of shift relative to each other. That's a low energy state. And so they do everything they can to maximize the regions where they're in the low energy state. So they become commensurate and low energy. And this is the last slide I'll show, is that this is a preliminary result from our simulations with this code, and you can see that you exactly get that. We started with something where this domain was large and there wasn't a lot of commensurate regions, and these ABBA domains with these interfaces form in the simulation. So we can predict this behavior, basically the picture that you saw on the previous slide. And we're doing some modeling now to understand the nature of this, and it's premature to talk about. So I won't talk about it, but this is really exciting that this just came out, is working well in the code. Okay, so let me summarize kind of what I've shown you. We talked about the major questions in multiscale modeling that I'm interested in, at least, I think are sort of key questions in this area. And the first one is, since we want to go to large systems, we need approximate, inexpensive models, as inexpensive as possible to model the atomic interactions. The problem is that once you throw out the quantum mechanics, you're throwing out much of the physics. And so then you have some fitted phenomenological model, and the question is how reliable it is. And let me just say that there's a very big difference between these interatomic potentials and constitutive relations that I said. Constitutive relations are almost always used to interpolate information. You do an experiment in a lab, and you stretch something, and then you put it in your finite element code, and you're only using it within the domain that you did your experiment on. And so as long as you're interpolating properly, it's reliable. These things, you fit, it supposedly will give you the response for any arrangement of atoms that you give it. But you only fit it to a very small number of configurations, and now you try and use it to simulate all sorts of things. So it's no wonder that half the time it doesn't do it right. And so it's very important to figure out how to figure out what's good for what. And this is, the Kim project is really a lot about trying to do that in a systematic way. Second is, once you have a function that depends on potentials, it's very, 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 very non-convex. And so we're just trying to get our heads around that with this idea of equilibrium maps, and developed an efficient way to scale with this kinetic Monte Carlo to use this information to predict long times. Then we just have directly the issue of going from small scales to large scales, from sort of an atomistic region to a continuum. And this is where this quasi-continuum method comes in. And what I didn't talk about is this kind of statistical mechanics-based ideas of coupling atomistic concepts to continuum. So we like to talk about stress at the continuum level, but at the atomistic level, I just have positions of atoms and velocities. How do you go from one to the other? It actually is a complicated question, and there are many definitions out there, but we were able to show that they all come from a single statistical mechanics framework. You start from statistical mechanics, non-equilibrium statistical mechanics, and then through controlled approximations, you can get all the definitions that are used out in the community. So that's sort of more fundamental type of stuff that we're interested in. Okay, that's it. Thank you very much.
We are running out of time. We'll maybe allow one question.
Elad, you talked about these timescale barrier of the rates and only being able to simulate very short time domains. People, for example, in the polymer community play around with the temperature to sort of like fake the effect of lower rates. Is there a generalization of those approaches, or like something along those lines that works in other areas of atomistic simulations?
So remember I mentioned that the work of Art Voder and the work on accelerating time. So we use this method called hyperdynamics, which reduces the barriers, right? Let me go back to that picture for a second. Oh, no. Oh, that was a bad mistake, because now I got to go through all this. Where did it go? Yeah, here we go. So hopping out of here, the barrier, it goes like e to the minus barrier over kt, right? So two obvious ways to speed things up: reduce the barrier, which is what this does, or increase the temperature. And so Art Voder has another method called temperature accelerated dynamics, which is exactly based on that idea. And it is a systematic way of doing it. It assumes transition state theory, which means that your system spends a lot of time vibrating in a basin before hopping out. I mean, and if you live in that kind of a system, then you can make a systematic argument. What actually happens in that method is, because you have to be careful. If you accelerate time, yes, you escape faster, but you may not escape to the right place that would have happened at the real temperature. And so what the method, the systematic way of doing it is figuring out for each jump that you do, extrapolating back and figuring out when that event would have happened at the original temperature that you're running at. And then you do this for a while. You collect information about all the places you can hop to. You extrapolate them all back to the real temperature, and you see which one would have happened first. That's the one that you choose to do. And so that's a more systematic way of doing it. Because otherwise, we did something similar looking at interfacial interpenetration of polymers, and we just turned the temperature up, because otherwise we couldn't see anything. And we did, in that particular case, it was completely uncontrolled. And we did try to run a few cases lower and see that we get qualitatively the same behavior, but that's a dangerous game to play if you don't really know.
Okay, I think we should end here and have another seminar next time. Okay, let's end.